In this video, I will show you how to easily animate a flexible part using finite element simulations calculated with SolidWorks and exported to Blender to be animated with the Shape Keys tool. I regularly publish animated 3D models on Sketchfab, in particular watch movements. These mechanisms include not only gear wheels, but also flexible structures. The first example where you can find an animated spring is in this model of the DSTB, a deadbeat seconds complication by Arnold and Son. The second example is found in the moon complication FB1L by the chronometry Ferdinand Bear 2. You can see that this flexible element is central to this wristwatch. The example I will use to illustrate how this is done is a compliant mechanism that is freely downloadable from printables.com. These are compliant forceps that are printable by polymer additive manufacturing. After downloading the STL file, the first thing to do is check the quality of the mesh. If necessary, you can reduce the size by remeshing. I'm going to skip this step because it is not the purpose of this video. The STL file can be imported directly into SolidWorks like this. Note that the STL version I'm using has been remeshed using MeshLab. It's a good habit to take the time to rename models properly and to make regular saves. I'll be doing that throughout this video. First, we need to choose a suitable material for these forceps. In principle, they are intended to be produced with polyethylene terephthalate PETG. In the SolidWorks library, we can choose a material with rather similar mechanical characteristics. We then define fixed geometries and external loads. Let's fix one of the surfaces of this flexure hinge. For the loads, the easiest way is to apply symmetrical forces to the shanks. The last step is to create the mesh before we can run the simulation. The mesh parameters are intentionally chosen coarse to speed up the calculation. We can now run the study. Note that the video has been accelerated only slightly. The calculation only took about 10 seconds. Hey, voila! We can now analyze the deformed result and adjust the parameters as required. Here, we don't want the parts of the locking mechanism to come into contact. We've now completed the work with SolidWorks. All that remains to be done is save the two models generated, the undeformed and the deformed forceps. The format we are interested in is VRML. We save both files with the WRL extension. VRML is a standard file format for representing three-dimensional interactive vector graphics. It is of course supported by Blender, but it is also possible to view the files we have just created directly in Windows. This looks all right. We can now move on to the second part of the process, which takes place in Blender. This is Blender. First things first, we're going to configure the workspace and remove the default cube and other unnecessary elements from the environment. I like it better in this configuration, at least for what we're interested in today. One after the other, we're going to import the two VRML files we've just created with SolidWorks. These are the non-deformed forceps. The orientation is correct. We keep only the useful data. We proceed in the same way for the deformed forceps. Everything is now ready to join these two objects using Shape Keys. Select both objects using Shift-click. Click on the Object Data Properties tab. In the Shape Keys panel, click on the pull-down menu to display Shape Key Specials. Click on Join as Shapes. In the list view, you should now see two new shape keys. The reference key is the basis. Depending on the order in which you shift-clicked on the two objects in the previous step, this reference is one or the other of these objects. In the present case, the reference is the deformed object. Next to the second shape key, there is a value which is currently set to 0. This value indicates the influence of the key used for blending between the shape and its reference. Click on the second shape key to display the relative shape keys options. Here is where the magic happens. By sliding the value bar, you can define the current weight of that shape in the mix. Click on the animate property symbol to the right of the value bar. This creates the first keyframe in the animation. Before proceeding with the animation, it is best to hide the static object from the scene. I'm going to fast forward through the animation of this object because I believe you get the idea. Here's the finished animation running in a loop. Open, close, open, close, open, close. Oops, save it. Sorry, I got captivated. Let's do one last little thing with this model. We give it a base color, blue. We click on the Material Properties tab and choose some blue with the color wheel. That's it. As I publish my models on Sketchfab, I greatly prefer to use their physically based rendering tools. We can now export the animated 3D model we have just created with Blender for transmitting and loading 3D models in web applications. A standard file format is glTF, or GL Transmission Format. Take a moment to review the different save options. Here, we're only going to transmit the visible animated model, of course with its shape keys. We've finished with Blender. Let's check the exported glTF file. Perfect. Aren't you impressed? In just a matter of minutes, starting from an STL file downloaded from the internet, we were able to create an animated 3D model. Here is the version I've uploaded to Sketchfab. And if you'd like to go one step further, here is the observable notebook in which I've embedded the 3D model using the JavaScript library three.js. Here you'll find the Blender file shown in this video, as well as the exported GLB file. It was a pleasure to help you, Christoph.